Hello. In today's lecture, we're going to be starting on the new chapter called Computational Classical Mechanics. So we have started a little bit on this previously when we looked at first order and second order differential equations. And we saw that in some cases we could solve those. So they were simple enough to solve. And we took a look at the solutions. Now for computational classical mechanics, we're going to be looking at some problems that can't be solved analytically. So the differential equations are too difficult to solve. So most of the time, they will be non-linear. So we can't use those methods we learned before, or they could be something else that's making it too difficult to solve. Yeah. So let's take a look at the general method that we're going to be using to study these systems, and then we'll look at two examples to start off with. Those being the simple pendulum and the mass on a spring. Okay, so firstly, what is the general method that we'll use? Okay, so we're trying to solve the second order differential equation given by Newton's second law. So we have F is equal to ma, and we know that a is the acceleration, so that's the second derivative of position. So m, let's say x double dot. Okay, so if we provide a force F, then this will be a second order differential equation with x. Okay, so we want to solve for x of t. Okay, or something similar, depending on what we're working on. Okay, so for some forces, especially linear forces, like Hooke's law, this is very easy to solve. We can use those methods that we looked at previously. But in some cases, this will be non-linear, and so we can't use those methods anymore. For example, the simple pendulum, which we'll see later. So what we do is we resort to some computational method to approximate the solution. Okay, so how do we do that? Well, the way we do it is by taking this second order differential equation, so a single second order differential equation. Okay, and we break it up into two first order differential equations. Okay. Yeah, because the second order differential equation can be quite difficult, but if we break it up into two first order differential equations, we know how to solve those. We can use either the Euler method or the Runge-Kutzer fourth order method to solve those two. Okay, so how do we do that exactly? Well, we introduce another variable, v, for the velocity, and this is going to be dx by dt, of course. And we include this so that we can separate this into two first orders. So v equals dx by dt, that's going to be our first equation. And then the second equation will be f over m is equal to dv by dt. Okay. So we see that we've got two first order differential equations, one of them being dx by dt equals v, and the other dv by dt equals f over m. And we see that they are coupled because the first one and the second one, they have some variables in common. In particular, we've got this v in common, but also the f could depend on v, could depend on x, or it could depend on both. Okay, so these are two first order differential equations that are coupled. So we've got two first order differential equations that are coupled. And by coupled, we just mean that they have some variables in common linking the two. Okay, so the typical thing that we're going to be doing is taking these and solving them computationally. So the first one, the dx by dt, we're going to write that as delta x over delta t is equal to v. And then this is going to give us x n plus 1 is equal to xn plus v delta t, like we had before with those other first order equations. And then the second one, delta v by delta t is equal to f over m. And then from here, we can get vn plus 1 is equal to vn plus f over m times delta t. Okay, so we have this simple updating procedure. Okay, so it's very similar to the updating procedure we had for the Euler method. But here, instead of just updating x, we're updating x and v. And notice that this v appears in this updating here, and maybe f could depend on x and v as well. Okay, so we see that the variables appear in both. Yeah. And then, of course, we have Tn plus 1 is equal to Tn plus delta t. So we can update the position, we can update the velocity, and we can update the time. Yeah, and then we just repeat this procedure, and then that will generate our solution. So we'll have the function x of t being generated, as well as v of t, okay, in case we need that. Okay. Okay, so this process is very similar to the idea of Hamiltonian flow on phase space. Okay, so we will look at this later on in the in-person lectures, but this procedure of updating the position and velocity, given the time increment, is very similar to this idea called Hamiltonian flow. Okay, so you will learn about this later on in your classical mechanics, but just briefly, we imagine phase space as this two-dimensional space, if we're working in one dimension, where along the one axis we have the position, on the other axis you typically have momentum, but in our case we're going to be dealing with velocity, so just v. But usually we speak of momentum, P equals mv, but we're going to be working with just velocity here. Yeah. So this idea of Hamiltonian flow is we start at some point, x naught, v naught. So this is our initial point or the starting point of the system. And if we let the system just evolve in time, like we just let the ball roll down the hill, or we let the spring oscillate, or we let the system do whatever it does, then this point will move through the space to some final point, xf, vf, like that, along some particular path. And then at each point along the path, the system will be in some state. So it will have some position and some velocity. So at each point in this phase space, we know the system's position and velocity. So I'll put that down as x and v. Okay, so at each point we know the system's position and velocity, and that's all we need to characterize the system. So that's all the important stuff that we need to know. Anything else that we want to know about the system, we can find using these two variables. For example, if we want to know the kinetic energy, well, we know the velocity, so we can work out the kinetic energy. If we want to know the potential, we've got the position, so we can find the potential. So anything of interest can be found from this particular point. Okay, so this updating procedure that we have here with x and v is the method by which we take a given point and we move to the next point in phase space. Okay, and then that would be the next point of the system with this position and velocity. Okay, so if something's moving, the position will change and the velocity will change along that curve. Okay, so as the system evolves in time, okay, quite similar to how we spoke about time evolution in quantum mechanics. It's very similar in this case. So as the system evolves in time, the systems point in phase space moves along the path. Sorry, the point in phase space moves along the path. Okay, so for example, this path over here. So we start at x naught, v naught, and then as the system evolves, it's going to move along the path. And it moves along given some time t. Okay, so we'll do a quick example. It's not necessarily a derivation, but it's a good example to show the general procedure of finding this time evolution. And we'll see that it's very similar to what we did in quantum mechanics. Okay, so everything we learned from there, we can apply to this as well. Okay, so we'll look at the example of a harmonic oscillator. Okay, so we know that for a harmonic oscillator, we have f is equal to minus kx. That's just Hooke's law. Okay, so we've got the restoring force there. And then we can use Newton's second law to find the equations of motion. So F is going to be mx double dot is equal to minus kx. We can take everything to one side. So we have mx double dot plus kx is equal to 0. Now we can divide through by m. So we have x double dot plus k over mx is equal to 0. And typically we replace this k over m with the angular frequency omega. So omega squared is k over m. So finally we get x double dot plus omega squared x is equal to 0. Okay, so we've seen this before, but that's roughly what we do. Given the force, we can then find the equations of motion. So the second derivative of x. Okay, so we know how to solve this using the using what we know about second order differential equations, but now we're going to use this separation, over here. So we're going to use the separation here by including this velocity term v to separate it out into two first order differential equations. And we'll see how that's related to this idea of phase space. So we won't solve it in this lecture. We'll do that in the next in-person lecture. Okay, but this is just to give you an idea of what's coming. Okay, so it's that's so dv by dt is our force. So F over m, remember. Okay, so F over m, that's going to be this x double dot, which will be minus omega squared x. Okay, so just look at that above there. And then dx by dt will be v. Okay, so instead of the second order differential equation that we saw last time, so second order differential equation, using this separation approach, we now have two first order equations. Okay, now notice how they are coupled, like we said before. So the dv by dt part that has an x and the dx by dt that has a v. So what we can do is write this in a bit more of a suggestive way. So we're going to write this as a matrix equation. Okay, since everything is nice and linear, so matrix equations make sense here. So we're going to write this as dv by dt as the first entry, dx by dt as the second, and this is going to be equal to some matrix times v and x, like that. Yeah, so what are the components of the matrix going to be? Well, when we multiply this out, we should get back to the original equations above there. So we can imagine this first row being 0 and then minus omega squared, because if we multiply this first row by that column vector, we're going to get 0 times v and then minus omega squared x. Yeah, and then that gives us the first equation. And then for the second equation, we're going to get 1 and 0. Because if we take the second row times the column vector, we're going to get v, which is that second equation over there. Okay, so these terms don't have to, they don't have to be linear equations, but that does make things a bit easier. But over here, we see that this is linear, and so we can separate it out like this. Okay, but we'll see for the simple pendulum that we can't write it like this because those aren't linear. Okay, but we can still solve them computationally. Okay, so let's just make a little note of that. The equations are linear. So remember what linear means. So our variables appear linearly. In other words, just scalar multiplied and then added together. So for the first one, we just have x appearing on its own. So we don't have sine of x or x squared or anything like that. And then in the second equation, we have v by itself. So no v squared or sine of v or log of v or anything like that. So we say that they're linear. So these equations are linear. And so we can use matrices. Right, if they weren't linear, then of course we couldn't do this. But the nice thing is we can work with these matrices. So we can take this d by dt outside, okay, because the d by dt will just act on each component. Right, that's how we can just define it. So d by dt, and then we have v and x is equal to our matrix here, 0 minus omega squared, 1 and 0, v and x. Okay. Now notice this column vector with the v and the x, that is very similar to this point in phase space. Remember, a point in phase space here, here we said was x and v. So the position and the velocity gave us a point in phase space. Here we have something similar. So this can be thought of as like a vector in phase space. Okay, so to make it more like what we have here, we can just swap some things around. So we can write this as d by dt xv is equal to 1, 0, 0 minus omega squared. Oh, sorry. Made a mistake here. That goes the other way around. Okay, so we have this here. So dx by dt, that's going to be v, and dv by dt, that's going to be minus omega squared x. Okay, so now this x and v, we can think about it being as like a vector in phase space. So we've got our x and our v, and given some point x, v, we have ourselves this vector or column vector given by that. And we see that d by dt of this vector, so the change in this vector, so let's imagine it like this. So going from one point to another, we have this change. Okay, from there to there. We can think of this as going from t0 to t1. Okay, so at time t0, we're at this point. Then at time t1, we're at another point. And going from the initial point to the final point, that's our change vector. Okay, and we see that in doing so, going from this point to this point is the same thing as multiplying our original vector by this linear transformation. Okay, so the action in going from, let's say, the initial point to some final point is done by this matrix multiplication. Okay, so if we multiply by this matrix, that moves us from our initial point at some t0 to some later time t1. Okay, so we can write this as d by dt of our x and v is equal to some matrix M times x and v. Okay, so on the left-hand side, we see that the change in the vector, so how does the vector move from the initial point to final point, is the same thing as m times xv. Now, if we imagine this not as a matrix equation, but instead as a normal standard differential equation, something like dy by dt is equal to lambda y. It's very similar. So we have d by dt of something is equal to some multiple of that thing. So dy by dt is lambda y. And we know that this gives us a solution. Y is equal to some constant a, e to the lambda t, where a is our initial part of the initial condition. Because when we substitute t equals 0, we just get a. So we can write this as y is equal to y0 e to the lambda t. Okay, now I'm just going to rearrange this slightly. I'm going to write this as y is equal to e to the lambda t y0. So we can imagine finding y is the same thing as taking our initial y0 and multiplying it by e to the lambda t. This is very similar to what we did with the quantum mechanical time evolution. Remember, we had psi of t is equal to e to the minus r t over h bar times h psi naught. We had some operator acting on the state, and that gave us the time evolved state. So again, very similar to this. This is the quantum mechanical version, and we'll see that we have the same thing for this case. We have that x and v is going to be equal to e to the m times t acting on the initial state. Okay, and then this gives us this idea of the Hamiltonian flow. So we can start at some point x0 v0, somewhere in our phase space. Let's just go back to the picture here. So somewhere in the phase space at x0 v0, we multiply by this time evolution operator, okay, similar to the quantum mechanical one. We multiply by this, and we get x and v, which is the state after some time t. And then just repeated action of this will then move us through phase space or move us through time. So this time evolution operator moves us through phase space in time. In time t. So if we increase t, we move to the next state. Okay, so this was just a brief introduction on how we get to this time evolution, provided that these equations are linear so that we can write them as matrices. So just as a little bit of homework, working with these, let's write this down here. So homework. Okay, so number 1, solve this x double dot plus omega squared x equals 0. Given x at 0 is x naught, and y at 0, sorry, not y, v at 0 is v naught. Using those methods we looked at before, so using the standard methods for second order differential equations. Okay, so remember, you find the characteristic polynomial, you get your lambda values, substitute them in, and then you solve for those constants given the initial conditions. So do that. And then once you've solved this, find your x of t and v of t. So find x of t and v of t. Okay, and then number 2. Okay, solve the following matrix equation. So we're going to have x and v is equal to what we had here. For this matrix M, the 0, 1 minus omega squared 0. So that will be e to the t, 0, 1 minus omega squared 0, acting on x naught, v naught. Okay, so do that part for homework, and finally compare the two solutions. Yeah, and then just note for this exponentiation of the matrix, of course, you're going to have to diagonalize it. So whenever we take functions of matrices, we need to diagonalize the matrix. So diagonalize the matrix, then take the exponential. Okay, so I will provide the full working as a PDF on the Learn page. Yeah, but first try it out for yourself, and then you can take a look at the solutions. Okay, so this is how we can solve these linear differential equations, okay, using this time evolution operator, if you want to call it that. However, we're going to be mostly interested in the computational side. Okay, so let's have a look at that with our first example on the simple pendulum. Okay, so imagine we've got ourselves a simple pendulum. So we've got a mass m attached to a rope length L. Okay, it's making some angle theta, and we want to study the dynamics of this system. Okay, so first of all, there are a couple forces acting on this. The first one being gravity going down, so mg, and the other one being tension that is acting through the rope. We can call that T. Yeah, so with a bit of trigonometry, we can find the net force acting on the system. So the net force will be something like that. Okay, so with all these angles and lines given, noting that this is a right angle triangle, you can use a bit of trig to find the following two equations. Okay, so I'll leave that for homework. But we have that the tangential force, so this force here going tangent with the F net, that's going to be F tan is going to be minus mg sine theta. Okay, so that's the tangential one. And then the radial one, that's in line with the tension there. That's going to be F radial is equal to mg cos theta. Okay, so we've got the tangential force in line with the F net and the radial force in line with the tension. Okay, but since we're looking at the F net, because the radial forces will, of course, balance out because the mass is not moving in the radial direction. It's only moving in the angular direction. So we're only interested in the first force, the F tan. Okay, so using that, we can write out the equations of motion. So F is equal to ma, of course. The acceleration will be ml theta double dot is equal to the force, but that's going to be minus mg sine theta. Okay. Yeah, so we're working with this angle theta over here. Yeah, we can divide through by ml, and we arrive at theta double dot is going to be minus g over l sine theta. And just note that this is a second order non-linear differential equation. Second order non-linear differential equation. Okay, so since it is second order, that makes things already difficult. Now we've got this non-linear term, which means we can't use those methods we looked at previously, because those were only for linear second order differential equations. And this other method that we've looked at now with the separation into two first order differential equations, that is also going to be difficult because of this nonlinear term. Okay, so this nonlinear term is making things very complicated for us. So we're going to resort to the computational method. Yeah, so let's separate this out into two first order differential equations because that makes things slightly easier, but then solving them we're going to have to do computationally. Okay, so we introduce our new variable. Like previously, we included v as dx by dt. Here we're going to introduce omega as theta dot. Okay, so that's typically what we do for angles, where omega is the angular velocity. So if theta is the angle, omega is the angular velocity. So angular velocity. Okay, so with that included, we can write this as two first order differential equations. So omega dot is going to be theta double dot because omega is already theta dot. So this is going to be minus g over L sine theta. And then theta dot, we define that already to be omega. So this is just by definition. Yeah, so we've got our two first order differential equations. And again, it's still nonlinear because of the sine theta. So again, still nonlinear. Okay, so we can't use that matrix method that we had before, because remember, we can only work with those matrices if things are linear. Okay, so these are nonlinear equations, so we can't use matrices. So instead, we resort to a computational method. So we can solve these two computationally. Okay, so it's exactly the same as solving a single differential equation, but now we just have two of them. Okay, so let's set up a quick program that can solve these. So we need some initial conditions. So just as an example, initial conditions. Let's say omega is 0, so it begins from rest, and theta is pi over 4. So it starts out at 45 degrees from the vertical, sorry. Okay, so let's write out a quick program. So we can import numpy as np. We won't do the plotting in this lecture here. I'll save that for the in-person lectures so we can see what it looks like on the computers. Okay, so import numpy as np. We can set our initial values here. So instead of omega, I'm just going to write it as a w. Okay, but we know that means omega. So that's going to be 0. And theta, I'm just going to spell out as theta. Yeah, that's pi over 4. So np.pi over 4. Okay, initial t, that's going to be 0. Time step, let's say h is 0.001. Yeah, of course you can set that to something else. Okay, so it's a bit of trial and error finding this h value, but something sufficiently small like this, that should be perfectly fine. Okay, so we've got our initial values there. Let's run this program for, let's say, 2 seconds. So while t is less than 2, let's do the updating procedure. I'm going to do this using the Euler method. Please feel free to try out the Runge-Kutta fourth order method as well. Yeah, some extra practice. Okay, so let's update our w. So w plus equals, remember how w was, so here I'm just writing it as w, remember it's omega. So omega is theta dot, so we can update omega by multiplying by theta times dt. Okay, so just a little side note, remember omega was d theta by dt, and then omega dot, was minus g over L sine theta. Yeah. And then that was our theta dot. Okay, so those are the two equations. So omega we can update using the second equation here. So it's going to be minus g over L sine theta. Times h. Oh, sorry, I'm writing theta. That should be np dot sine theta. Okay, and then this g and L, we can just define that up here. So maybe just squish it in at the top there. G is 9.8, and L, let's say, is 1 meter. Okay, so we can just add that to the top with our constants. Okay, times h. Okay, that's separate. And then we can update theta plus equals. So theta dot is just omega, so we can update it as w times h. And then we can update our time. So t plus equals h. Okay, so that is exactly what we did previously with the Euler method for a single differential equation. But here, just note that we have to do the updating procedure twice because we have two differential equations that we are solving simultaneously. So we do the updating twice. Because we have two first-order differential equations that we are solving simultaneously. Okay, here we're just updating the values. We're not using them for anything, but later on when we want to study the energy of the system, for example, or we want to plot what this angle looks like over time, then of course we need to save these values in a list. Okay, but just for now, we just want to see the updating procedure. Later on, we will save the values and then analyze them afterwards. Okay, so this is the general idea of what we do for these systems. Let's take a look at the next example of a simple harmonic oscillator. So just a mass on a spring. Yeah, so this is just the general idea of what to do. And then in the tutorials, it goes into a bit more depth of analyzing what happens after we collect all this data. So once we have the position and velocity information, we can then look at how the energy changes, if there's any loss in the energy, and so on. Okay, but we'll save that for the tutorial. Okay, so mass on a spring. So we have the following setup. Some mass m on a spring with spring constant k. So first thing we need to do is find the equations of motion. So very similar to what we had before. We know F is equal to ma. So mx double dot is equal to minus kx. Again, this is Hooke's law. Okay, so that was quite easy to do. So the problems that you're going to get in the test and exam will be fairly similar to this. So objects sliding down ramps, springs, pendulum, spring pendulum, right? Anything like that, but nothing too difficult. Okay, so we have Hooke's law given in differential form like this. We can write this as x double dot equals minus omega squared x, where we have defined this omega squared as k over m. Okay, so we have our second order differential equation. We would like to write it as two first order differential equations. So again, we introduce this variable v, that's going to be dx by dt. Okay, so we can rewrite this first equation that we have here, not as x double dot, but as dv by dt. So dv by dt will be minus omega squared x. Okay, so we have our two first order differential equations. One of them dv by dt, and the other one dx by dt, where that one is just by definition. You don't have to work anything out for that. Okay, so let's just list them here as number one. dv by dt is minus omega squared x. And number two, dx by dt is v. Okay, so very similar to what we had before. And in this case, they are linear. So we could use that method that I set for homework. Yeah, but let's do this computationally. So we can import numpy as np. We can set our initial conditions. So let's say that it starts out at 1 unit away from equilibrium with velocity 0. So x is 1, v is 0, t is 0. We need a time step. So let's say h is 0.001. And let's do this for 5 seconds. Okay, you can mess around with this in your own time. So you can change the final time and see what kind of graphs you get. Okay, but here we're just going to do it for 5. And we also need to define omega, but let's just say omega we can write as w. Let's just set it to 1. Okay, you can change that and see what happens to your graphs. Okay, so remember this w, that's going to be our, let's write that curly, that's our omega. Okay, let's do the updating procedure now. So while t is less than 5, we said we were going to run this for 5 seconds. Let's update our v. So v is updated using this minus omega squared x. So let's do that first. So v plus equals minus w times x. Okay, that's from the first one. And then remember to multiply by our time step h. Okay, and also this omega squared or the w squared, we could have written using that exponential form as well. Okay, both are fine. And then we need to update x. How do we update x? Dx by dt is v, so we can updating it using v times our time step. So v times the time step. And then, of course, we need to update our time. So t plus equals the time step. Now, again, like in the previous example, I'm not going to save these values because we're not going to look at the analysis in this lecture. We will look at the analysis in the tutorial. Okay, so we'll leave it at that for today. In the tutorial, when we get back after the holiday, we'll look at all the analysis. So looking at the energy as a function of time, looking at if there's any loss in energy. So especially with this simple harmonic oscillator, we're going to add a damping term, and that will result in some energy loss. Then we're going to see how that affects the system. Okay, so we'll be doing that after the holiday. But please, during the holidays, I know it's your time off, but try to spend a little bit of time looking at this program and the previous program, and maybe making some plots to see what's going on. Okay, just in terms of the dynamics, everything else we will look at later. Okay, but again, it is the holidays, but if you do have any questions for me, please don't hesitate to email me. Okay, but then I'll see you afterwards.